Imagine a world where everything is the opposite, up is down, left is right, and matter is antimatter. This isn't just a mind-bending thought experiment, it's a fundamental part of our universe. Antimatter is real, and it's one of the most explosive mysteries in physics. Antimatter is like the mirror image of normal matter. For every particle of matter, there's an antiparticle with the same mass but the opposite charge. When matter and antimatter meet, they annihilate each other in a burst of pure energy. This makes antimatter both fascinating and incredibly dangerous. Understanding antimatter is crucial to understanding the universe. It could hold the key to unlocking the secrets of the Big Bang and the fundamental laws of physics. It could even lead us to new sources of energy beyond our wildest dreams. But first, we need to unravel its mysteries. So, what exactly is antimatter? It's not some exotic substance from a distant galaxy. It's all around us, albeit in minuscule quantities. Antimatter particles are like the evil twins of normal matter particles. They have the same mass but opposite charges. For example, the antiparticle of an electron, which is negatively charged, is a positron, which is positively charged. Similarly, a proton, which is positively charged, has an antiproton, which is negatively charged. When a particle meets its antiparticle, they annihilate each other. This annihilation converts their entire mass into energy. This process is the most efficient energy release known to physics. This explosive reaction has captured the imagination of science fiction writers for decades. But antimatter is more than just a plot device. It's a real phenomenon with the potential to revolutionize our understanding of the universe and our place in it. The story of antimatter begins in the realm of theoretical physics. In 1928, British physicist Paul Dirac was working on a theory to combine quantum mechanics with Einstein's special relativity. His equations predicted the existence of a new particle, one with the same mass as an electron, but with a positive charge. At first, Dirac was hesitant to embrace this strange prediction, but the math was clear. 4 years later, in 1932, American physicist Carl Anderson observed Dirac's theoretical particle while studying cosmic rays. He called it the positron, and its discovery confirmed Dirac's bold prediction and opened up a new realm of particle physics. The discovery of the positron was a major breakthrough. It proved that antimatter was not just a mathematical quirk, but a fundamental constituent of our universe. This realization had profound implications for our understanding of the cosmos. Here's a perplexing puzzle. According to the Big Bang Theory, equal amounts of matter and antimatter should have been created at the beginning of the universe. But when we look around us, we see a universe dominated by matter. Where did all the antimatter go? This is known as the baryon asymmetry problem, one of the biggest unsolved mysteries in physics. If matter and antimatter annihilate each other upon contact, and they were created in equal amounts, then shouldn't the universe be filled with nothing but energy? There are many theories but no definitive answer. Some scientists believe that a slight imbalance in the laws of physics favored the production of matter over antimatter during the universe's first moments. Others propose that antimatter might exist in vast undiscovered regions of the universe. The search for the missing antimatter continues to be a major focus of research. Section 5. Taming the Beast. Studying antimatter. Studying antimatter is not for the faint of heart. It's incredibly difficult to create and even harder to contain. Because antimatter annihilates upon contact with matter, scientists have to develop ingenious methods to produce, trap, and study it without it being destroyed. Particle accelerators like the Large Hadron Collider, or LHC, are used to create antimatter. These massive machines smash particles together at nearly the speed of light. The energy released in these collisions can create minuscule amounts of antimatter. Once created, antimatter must be carefully confined. Scientists use magnetic traps to suspend antimatter particles and prevent them from coming into contact with matter. These traps use powerful magnetic fields to hold the charged antimatter particles in a vacuum, isolating them from the surrounding environment. Section 6. The ultimate energy source. The annihilation of matter and antimatter releases an immense amount of energy. This has led to speculation about antimatter's potential as a revolutionary energy source. In theory, a small amount of antimatter could power entire cities or even propel spacecraft to distant stars. The energy density of antimatter is unparalleled. A single gram of antimatter could release as much energy as the atomic bomb dropped on Hiroshima. However, harnessing this power is a monumental challenge. The production of antimatter is incredibly inefficient and expensive. It takes enormous amounts of energy to create even tiny amounts. Additionally, storing and controlling antimatter safely pose significant technological hurdles. While antimatter offers tantalizing possibilities, practical applications for power generation remain a distant prospect. Section 7. Antimatter in the doctor's office and other places. While antimatter power plants might be a long way off, antimatter is already being used in practical applications today. One of the most well-known uses is in medical imaging. Positron emission tomography, or PT, scans use positrons to create detailed images of the body's internal organs and tissues. In a PET scan, a small amount of a radioactive tracer that emits positrons is injected into the body. When these positrons encounter electrons in the body, they annihilate, producing gamma rays that can be detected by a scanner. These signals are then used to create three-dimensional images that help doctors diagnose and monitor a wide range of conditions, from cancer to heart disease. Beyond medical imaging, antimatter research has also led to advancements in materials science, computing, and our understanding of fundamental physics. Antimatter is a powerful tool for probing the universe at its most fundamental level. Section 8. The antimatter bomb. Fact or fiction? Antimatter has been a staple of science fiction for decades, often portrayed as the ultimate weapon of destruction. From Star Trek's warp drive to the explosive antimatter bombs in countless sci-fi films, antimatter has captured the imagination of writers and audiences alike. But how much of this is based on reality? While it's true that the annihilation of matter and antimatter releases an immense amount of energy, creating a practical antimatter weapon is far beyond our current capabilities. The amount of antimatter required to build even a small bomb would be astronomically large, and producing and storing such quantities safely is currently impossible. Moreover, the cost of producing antimatter is astronomical. It's estimated that producing a single gram of antimatter would cost hundreds of trillions of dollars. So while the concept of an antimatter bomb might make for exciting science fiction, it remains firmly in the realm of fantasy. Section 9. Antimatter and the Big Bang. The existence of antimatter has profound implications for our understanding of the universe's origins. The Big Bang theory posits that the universe began from an extremely hot, dense state. In the first fractions of a second after the Big Bang, the universe was a seething cauldron of energy and particles, including matter and antimatter. As the universe expanded and cooled, matter and antimatter should have annihilated each other, leaving behind nothing but a sea of photons. However, we observe a universe dominated by matter. This suggests that a slight asymmetry must have existed in the early universe, favoring the production of matter over antimatter. This baryon asymmetry is one of the most significant unsolved problems in cosmology. Scientists are actively searching for explanations for this asymmetry, hoping to shed light on the fundamental laws that govern the universe. Section 10. Unlocking the universe's secrets. Antimatter is not just a curiosity, it's a key to unlocking some of the universe's deepest secrets. By studying antimatter, we can test the fundamental laws of physics and probe the nature of space, time, and matter itself. For instance, experiments are underway to determine if antimatter experiences gravity in the same way as matter. If antimatter falls up instead of down, it would overturn our understanding of gravity as we know it. Other experiments aim to measure the properties of antimatter particles with unprecedented precision, looking for even the slightest deviations from their matter counterparts. These experiments could reveal new physics beyond the standard model, our current best description of the subatomic world. They might even provide clues about the nature of dark matter and dark energy, two of the most elusive mysteries in modern astrophysics. Section 11. The Quest for a Theory of Everything. The ultimate goal of physics is to find a single, elegant theory that explains all the fundamental forces and particles in the universe. This theory of everything would unify Einstein's general relativity, which describes gravity, with quantum mechanics, which governs the subatomic world. Antimatter could play a crucial role in this quest, by understanding why the universe is dominated by matter and how antimatter behaves under extreme conditions. We might gain insights into the fundamental laws that govern the cosmos. The study of antimatter is a journey into the unknown. It challenges our assumptions, pushes the boundaries of our technological prowess, and offers a glimpse into the fundamental building blocks of reality. As we continue to explore the mysteries of antimatter, we inch closer to unraveling the universe's most closely guarded secrets.